Hello my dear students, welcome to Deeksha Karnataka YouTube channel, and in today's lecture I am going to discuss all the important derivations for your final board exam. So in this lecture we are basically going to cover all the important derivations from your question banks, from your previous year questions, from the model question paper. So everything will be covered. So if you watch this single derivation lecture, your 15 marks will be sorted, right? So in your how many derivations you have to answer? You have to answer 3 derivations. Each derivation consists of 5 marks. Sometimes there may be some 2 marker or 3 marker small derivations. Some of the derivations I have covered them in my 2-3 marker videos. So if you have not watched them, after the end of this lecture you can go and check that out as well. Now remember, this is the one video where if you watch all of your derivations will be covered. That is my guarantee. Okay, now let's start with the lecture. First we will obviously start with the first very simple derivation. Derive the expression for electric field at a point due to an infinitely long, thin, uniformly charged straight wire using Gauss's law. So obviously thin, uniformly charged wire is there. And remember, for derivations, diagram, if there is a diagram, you have to draw the diagram. There is no other way. Okay, some derivations they will mention the diagram, draw the diagram. Some cases they will not mention. For example, here they have only asked you to derive, but they have not mentioned to draw the diagram. But diagram is obviously important if you are doing the derivation. So derivation means diagram is compulsory. Please pardon me, I am drawing using my hand. If you are using any scale, use that to draw the diagram. Now here it is the simple charged wire. Okay, we are assuming it is positively charged, and when there is a line charge, what do we consider? We consider the line charge density. Line charge density means charge per unit length. Okay, charge per unit length is called line charge density, which is basically you take the total charge, you take the total length, divide it, you get the line charge, or you take 1 meter of the length and you calculate how much charge is there in that 1 meter of length. That is also line charge density, lambda. Okay, now we are trying to find the electric fields at a distance small r. Now what you have to do, remember the steps. Even though the diagram you can draw it according to your own suitability, but remember that when you are writing, this point P comes first. This point P comes first. Okay, so we are trying to find the electric field at a distance r from the wire at point P. Now let us construct, you have to mention, let us construct a Gaussian surface. Let us construct a cylindrical Gaussian surface of radius r and length L. Okay, so what we are doing now, the step you have to be careful. You are not first drawing the cylinder, then you are pointing the point. So remember this step. Okay, even though while drawing the diagram you can draw the cylinder first, that is a easy way to draw the diagram. So you can draw the cylinder first, then you point the point P, but when writing you have to remember that based on the location of this point P, you are taking the cylinder. Okay, the length as given in the question, so length is given as small l. And if you want to download the PDF of today's lecture, obviously you have to join the WhatsApp channel. Many times students ask me, sir, where is the PDF, where is the PDF, how to download the PDF. You don't have to do anything. Only one thing that is necessary from you is join the WhatsApp channel. The link of the WhatsApp channel given in the description section of this video. Click on there, and we have shared the drive link. All the files will be uploaded in that particular drive. Also from time to time, those who are joining now, we will be sharing the drive link once more. So once you get the drive link, bookmark it, and from there you can download all the PDFs of the Endgame series there right away, right? Physics, chemistry, maths, biology, Kannada, English, all the subjects. There is only one single folder, and you can download the link, but the link will not be shared on WhatsApp, on YouTube. It will be only shared in our WhatsApp channel, so don't forget to join the WhatsApp channel, right? So the radius of the cylinder is r. Now what? Next point. So suppose the electric field, obviously electric field will be radially outward. So say this is the electric field, and we take a small area ds. ds and electric field are in the same direction. Okay, so electric field and ds are in the same direction, so that means ds is also perpendicular to a surface, so that means E dot ds simply will be a scalar quantity. Now anyway, that will come a little bit later. So from Gauss's law, okay, from Gauss's law, whatever you are comfortable with, from Gauss's law, E dot ds integration E dot ds equals to charge enclosed divided by epsilon naught, right? Flux is electric flux coming out of this cylindrical Gaussian surface is given by E dot ds equals to q enclosed by epsilon naught. Now what is q enclosed over here? So line charge density is given here lambda. The length that we are considering over here is L. So for unit length the charge is lambda. For length L the charge will be simply lambda into L divided by epsilon naught. Okay, length into line charge density will give you the total charge, right? So total charge is lambda into L. So you can write it over here because q enclosed is given by lambda into L. Okay, now what? Now due to symmetry, the language is almost same for all Gaussian Gauss's law related questions. Okay, due to symmetry, E is constant on the curved surface of the cylinder. E equals to 0 for top and bottom surfaces. So it is E equals to 0 on top and bottom means what? So E on this surface is 0, E on this surface is also 0. Because they are perpendicular, so E dot ds will be 0, so that means E has to be 0 on these two surfaces, okay? Because electric field will be radially outward for a point charge. Here you can consider it because it's an infinitely long charge. The electric field will always be outward, it will not be along the charged wire, okay? So that's why electric field from this and this surface will be 0. Now sometimes students ignore it. It's okay, but you should mention it if you have time, if you understand that electric field is 0 on these two surfaces. At least in the diagram if you mention, that will give a good impression on the teacher. Okay, now what? So again E is constant, that means E will be coming out of the integration, therefore E into close integration ds equals to lambda L by epsilon naught. Here ds is basically the area of the curved surface. Area of the curved surface of a cylinder is given by 2 pi r into L. Okay, 2 pi r L is the area of the curved surface, that is lambda L by epsilon naught. Okay, or E equals to 1 by 2 pi r L into lambda L by epsilon naught, or L cancels and you get 1 by 2 pi epsilon naught lambda upon r. Okay, I generally prefer to write it as 1 by 4 pi epsilon naught 2 lambda by r. Okay, so that this constant value says as constant. So this is the derivation, easy derivation, very simple. If you practice it once or twice, you should be able to answer it. But remember, practicing is very, very important. Without practicing, you may not be able to execute the same derivation in the exam. Starting from the diagram, you have to practice it at least twice. Next, derive the expression for electric field at a point on the axis of an electric dipole. So here, so axis, we will be doing both cases, axis as well as on the equatorial plane. So here is the dipole. So this is suppose negative charge, this is positive charge, and we are trying to find electric field at a point P. Okay, the distance of the point, say R, the length of the dipole is 2L. So this distance is L, this is also L. Okay, now if this distance is L, thus from the center the distance is R, so that means from the positive charge the distance will be R minus L, and from the negative charge the distance will be R plus L, right? Same distance we are measuring from the center. So if you minus L, you get the distance from the positive. If you plus L, you get the distance from the negative. Okay, now what is the electric field due to the positive charge? Electric field due to the positive charge is K charge divided by the distance, that is R minus L whole square. What about the electric field due to negative? Same formula, KQ by R plus L whole square. Now the direction is important, because as I mentioned, whenever you calculate electric field, the sign of the charge is not important, direction of the electric field is important. So due to a positive charge, electric field is away from, so this is E plus, and due to a negative charge, it will be towards the charge, so it will be in this direction for E minus. Okay, so E plus is away from, E minus is towards the charge. So what is the net electric field? So net electric field is given by E plus minus E minus, because E plus is closer, E plus is bigger than E minus, so that's why E plus minus E minus. Now put the values, KQ by R minus L whole square minus KQ by R plus L whole square. Okay, now not too much writing is required for this derivation, only if you can explain the diagram, that will be a bonus added advantage. So net electric field is, obviously K and Q is common, and we get 1 by R minus L whole square minus 1 by R plus L whole square. Okay, now KQ is common. In the division we get R minus L, R plus L, both had square, so square is common. Now we get R plus L whole square minus R minus L whole square, right? Cross multiplication, right? So we can now write it as, so if you see that the top portion is A plus B whole square minus A minus B whole square, which is a small formula that we have learned when we are very small kids, that is 4RL, 4AB. Okay, A plus B whole square minus A minus B whole square equals to 4AB. So that formula we have used, and in the division A plus B into A minus B, again another formula we learned when we are kids, so A square minus B square, right? And there is a common whole square over here, so that will also be considered. Now let us simplify this. So E net equals to K into 4 Q into L into R divided by R square minus L square whole square. Okay, now we know that dipole moment of a dipole is given by 2Q into L. Distance between the charges 2L into Q. Okay, so this is the dipole moment, so we will put that over here. So here we have 4QL, so that means it will be 2P into R divided by R square minus L square whole square. Okay, so P is this 2QL. Now we have to assume that for this given case, because the distance between the dipole is very, very small, so 2L is small, that means L will be much smaller than that, right? So R is very, very greater than L, so therefore E net will be equals to K 2PR divided by R to the power of 4. Okay, R to the power of 4. Why R to the power of 4? So we ignored this L square in terms of R square, because R is very, very bigger than L. That means L is smaller, so L square will be much smaller. So if you square a smaller number, that becomes much smaller. So that's why this is like this. So L square is ignored in terms of R square. Okay, with respect to R square. Now one of the R will be cancelled, and we get K into 2P divided by R cube. So E net final touch 1 by 4 pi epsilon naught 2P by R cube. Okay, K is Coulomb constant, which is 1 by 4 pi epsilon naught. So this is the derivation. Now remember that the direction is same as dipole moment. Okay, the dipole moment is from negative to positive. The net electric field is also in this direction. So if you add one more line, vectorial notation, you can add that E net is same direction as P net, dipole moment. Okay, now let's move on to the next question. Derive the expression for electric field at the point on the equatorial plane of an electric dipole. Some students find this little difficult, so we will make it easy as much as possible. So this is the dipole. Equatorial plane means the line or the plane which actually divides this dipole axis into two equal parts. So this distance is L, this is also L. Actually it is a plane, but we are taking a line. Okay, equatorial plane, even though they have mentioned equatorial plane, actually we are taking perpendicular bisector, which are same. Okay, now consider a point P on this line, which is at a distance say R. So we join this and extend. So say this is positive charge, this is negative charge. You have to join this line, and electric field will be along this direction. Okay, now remember that in case of negative charge, electric field is towards the charge, whereas positive charge is electric field is away from the charge. So this will be in this direction, this will be away from. So line joining the charges towards, line joining the charges away from. Okay, now you have to calculate the net electric field. So net electric field, you have to consider this line. To find the net electric field, you have to consider this line, and you have to take the component of these two vectors along this line. Okay, you have to take the component of these two vectors along this line. How to take the component? So for that you have to know that this angle, if this angle is theta, this angle will also be theta. Why? Because this is a perpendicular bisector. If this is a perpendicular bisector, we know that the perpendicular bisector divides the base by 2. So that means this will give you an isosceles triangle. That means this side is equal to that side. So this side say R dash and this side R dash, both are same. Okay, both R dash are same. Now both now if this angle is theta, then this is similar angle, so this will also be theta. And if this angle is theta, this angle will also be theta, alternate angle theta Z. Here they are forming like this parallel lines. So this angle will be this for the first one, and this angle will be this for the second one. Okay, so this is how you can say. Now what? So if you take the component, this will be cos theta component for the top one. Okay, this will also be cos theta component for the bottom one. This will be sin theta component for the top one, and this will be sin theta component for the bottom one. So along the y direction, the electric field will cancel each other. Along the y direction, the electric field will cancel. So we need to find the components. We need to find the component of electric field. Find the electric field along x direction. So this is x direction, this is y direction, right? Or x axis also you can mention. Now what is E plus? E plus is K Q by R dash square, electric field due to a point charge. This is R dash. So K Q by R dash square. Similarly, for a negative charge also the electric field will be same. Okay, magnitude wise both electric fields will be same. The directions are obviously it's not same, but magnitude wise same. And we are saying this equals to E in bracket C. Okay, so both, because their magnitudes are same, we are saying this is equals to this and say E. Okay, so now we are trying to find the net electric field. Net electric field is basically x component of this and x component of that, so both will be Ex plus Ex, that is 2Ex. Okay, or 2 into Ex. Ex is what? Ex is E cos theta. Okay, both of them are same cos theta component, so E cos theta is the net electric field. So 2 into what is E is this KQ upon R dash square into cos theta. Now put the values of R dash, put the values of cos theta, and your answer will be done. So net electric field is given by 2K into 2Q into divided by R dash. So from Pythagoras theorem we can say that R dash is actually equals to square root of R square plus L square. Right, this is L, this is R, so this from Pythagoras theorem, hypotenuse, and we have square of it, so it will be R square plus L square. Very simple, right? It will be R square plus L square. What about cos theta? So if you consider this angle, cos theta is base by hypotenuse, so base is obviously L, hypotenuse is R dash is this, so it will be square root of R square plus L square. So we can write this as K into 2QL divided by R square plus L square to the power 3 by 2. Okay, to the power 1 into to the power half, so it will be 3 by 2. Now what is this 2QL? Again 2QL is nothing but the dipole moment, so it will be R square plus L square to the power 3 by 2. So P equals to, mention P equals to 2QL. Okay, 2L is the distance, charge is any one of the charge, that is dipole moment. Now you can write that E net. Now you have to take the obviously the approximation, not approximation, actually it is very authentic, that R anyway is very greater than L, so E net, so you can ignore this L square and you can write E net equals to K P divided by R square to the power 3 by 2. L square is 0 now compared to R, so you can write Kp by R cube. Okay, square to the power of 3 by 2, right? Now you can write this as 1 by 4 pi epsilon naught P by R cube. Now if you see that here, net electric field is in the x direction, but the dipole moment, which is from negative to positive, this is the direction of dipole moment. So in this derivation, vector form is very important. So E net vector equals to minus 1 by 4 pi epsilon naught P by R cube. Now you have to mention the P vector and E vector are in opposite direction, that is why there is a negative sign. Okay, that line you have to mention. You have to mention why it is negative. Clear? Now let's move on. Using Gauss's law, arrive the expression for electric field at a point outside the charged spherical conducting shell. Also write the expression for electric field at a point on the surface of the same charged spherical shell. So let's see. Based on this, last year we have seen a numerical question. Maybe this year they might give this as a derivation. This is another very easy derivation. Spherical shell means only this much is material, remaining part is vacant. Okay, so this is the shell. Now radius of the shell is given by capital R. Okay, and we are trying to find electric field at a distance small r, say at a point P. So how to do that? Obviously Gauss's law. So and when you get this question, they might also ask you state Gauss's law and hence find. So Gauss's law, anyway, if it is not coming as a 2-3 marker question, they might give you the question in this derivation. Okay, so my circles are not exactly circle because obviously if I try to draw the entire full circle, it will go out of the board. So let me adjust it. Okay, now it is fine. So this is say point P. Okay, my point P was little far away. Now what you have to do, you have to find the electric field at this point. Now how to do that? Obviously Gaussian surface. Let us construct similar writing has to be same. Let us construct a spherical Gaussian surface of radius small r and r is greater than capital R. That you have to mention because you are trying to find electric field at the point outside the shell. Right? Now from Gauss's law we can write close integration E dot ds equals to charge enclosed by epsilon naught. What is charge enclosed? Charge enclosed is the total charge of the on the shell, that is capital Q. So from here again for symmetry, due to symmetry E is constant on the surface of the sphere. Okay, so again it will come out, any constant is outside the integration, so integration ds equals to capital Q divided by epsilon naught. Now ds is the surface area of a sphere, that is 4 pi r cube. Okay, 4 pi r cube of this Gaussian surface. Remember, not capital R cube but small r cube. Okay, so from here we can say capital E into 4 pi r cube equals to Q upon epsilon naught, or E equals to 1 by 4 pi. Sorry, my mistake. It is not r cube, it is r square. Okay, it is not r cube, it is r square. 4 pi r square. So 1 by 4 pi epsilon naught Q upon r square. Now you can leave your derivation over here, but I'll do a little bit more from there, so that in case last year the question came as a numerical, there they have mentioned surface charge density. Surface charge density was given. Now they asked you what is the electric field. How to do that? That also I will explain. Surface charge density means if you take a small surface area and unit surface area, the charge on that unit surface area is sigma. Now how to calculate the total charge if surface charge density is known? If surface charge density is known, total charge can be expressed as the surface area of the sphere, okay, surface area of the inner sphere times the charge density, which is sigma. So you can substitute it over here and you can simplify the values. So in terms of surface charge density, it is not necessary, it is not compulsory, okay, but if you remember the formula, that might be helpful for you to solve some numerical question in case you see the same numerical question is coming this year as well. So 4 pi capital R square sigma divided by small r square. So 4 pi cancels, and you get electric field is equals to sigma r square divided by r square epsilon naught. Okay, so this is the electric field on the at a point outside the sphere. The electric field is same on the surface of the sphere. Till surface everything is same. Okay, on the surface it is same value as this, and in just inside the surface electric field is 0. No charge is enclosed for inside portion, so electric field is 0 inside, but on the surface it is exactly equals to R equals to capital R. So electric field on the surface equals to sigma R square by R square epsilon naught. So R square cancels, and you get on the surface it is actually a constant which is given by sigma by epsilon naught. On the surface of a spherical conductor, electric field is sigma by epsilon naught, right? So remember that sometimes they ask you a question where they say that on the surface of the electric field is measured to be this value. What is the surface charge density? What is the total charge, etc. So in that case, you can use the electric field is given, sigma value you have to calculate. Then you can calculate the total charge on the sphere as well. Okay, so that is one thing. So if electric field is given on the surface, you don't need to use this formula. You can directly use this formula and calculate. Right now. So this is the second part. Remember, this is the second part. For second part, this is very essential. If you are using this formula, instead of small r, you have to use capital R on the surface. For the surface, it is not 0. Remember, on the surface of a conductor or surface of a spherical shell, electric field is not 0, but here you have to put small r equals to capital R. That's it. Okay, on the surface, small r is equals to capital R. If you substitute that, you will get the electric field on the surface. Now let's move on. Before moving on, those who are preparing for your KCET exam and worrying from where to study, how to study, for them we have launched KC 30, which is an exclusive 30-day crash course, online crash course, completely in English, and the batch is starting from 21st of March. What you will get in this crash course? You will get 30 days live online crash course, KCET previous year questions in with solution in detail. You will also get complete syllabus revision for PU1 and PU2. You will get chapter wise KCET PYQs as a form of quiz, so that you can attempt and check how much prepared you are for your KCET exam, and 10 full length KCET mock tests. You will also get 10 full length KCET mock test, and price of this crash course is only 2499. This is an exclusive price valid up to 25th of February. Now let's continue. Derive the expression for electric potential at a point due to a point source charge. This is one of the common derivation. It came last year. There is a chance this coming this year slightly small, but who knows. PU board has a tendency of repeating questions, so they sometimes try to catch students off guard. You will not prepare this derivation thinking that it came last year, but in PU board exam that is not a case. In some other boards there are some cases if it is coming in previous year, it generally do not come in the next year, but that is not true for PU board. PU board generally gives repeated questions year after year, so if this question came last year, there is no guarantee it will not come this year. Okay, so be careful about it. In 2-3 marker questions generally it does not repeat, but in 5 marker derivation questions it generally repeated multiple times. Okay, now let's see. So electric field, we are trying to find the electric potential due to this positive charge at a distance p. Now what is the definition of electric potential? Electric potential is defined as work done to bring a unit positive test charge from infinity to a point in electric field. So work done required to bring a unit positive test charge from infinity to the point. Okay, so from infinity to this point, whatever work you are doing, that is the potential of that point. Okay, the charge has to be unit positive charge. Okay, suppose, so this is our infinity. Okay, we are going towards infinity. Now infinity is something that we cannot obviously handle, so what we will be doing, we will take 2 points A and B, they are very close. A and B are very close. The distance between them is dx. Okay, and the distance of the charge, average distance from the charge to this point is actually x. Okay, the average distance from the charge to this point is x. Now remember, this charge will apply a force if you put a unit positive test charge over here. Okay, and that force is internal force of the system. You have to apply an external force to overcome that force and bring it closer. Now that force is dependent on the distance. That's why there is some sort of tricks are required. If it is independent of the distance, you could have used the old formula of work done equals to force into displacement and calculate it. But force is dependent on the distance. That's why we cannot solve it directly. We have to go in an indirect method. Okay, so what is the internal force? Internal force is actually the Coulomb's law KQ plus 1 divided by x square. Internal force acting on this charge at point A, acting on the unit positive test charge at point A. The internal force is given by Coulomb's law. Okay, so basically what does that mean? That when you are applying an external force to move this charge when it is located at point A, you have to apply exactly same amount of force as internal, but in the opposite direction. So internal force is trying to take it away, but you are trying to bring it closer. That means you have to apply a force in the opposite direction. That means it will be minus KQ by x square. So this much force you have to apply to bring it closer. Okay, so remember, do not ignore this negative sign. Negative sign is important, otherwise there will be a negative final answer will have a negative result, and you have to at the end you will say multiplying by -1 we get. So that is not correct, right? That is called stop gap. Okay, that is not accepted. Okay, now let us do one thing. You have to calculate the work done. What is work done? Work done to bring the test charge from point A to B. A and B are very close to each other. Dx is almost 0, very close to each other. So we can say that from A to B, the force is almost constant, and work done required is basically the external force that you are applying times the displacement that it is undergoing, that is dx. Dx is very small, so we can say that external force is also external force required is also very same. So minus kq by x square into dx. This is the work done to bring the charge from A to B. Now we are not satisfied with bringing the charge from A to B. We have to go to infinity and bring it till point P. So for that, what you have to do? To calculate total work done, we have to integrate this starting from infinity till our point P. Okay, and that is basically dAB. Okay, we have to integrate this work done to calculate the total work done, that is the potential. Okay, so that is equals to infinity till point R. Distance, initial distance was infinity, final distance is R, and if you put that value, minus kq by x square into dx. Now k is constant, charge is given in this particular case, so charge is also constant. So k and q coming out of integration, we have dx by x square and infinity till R. So that is equals to minus kq. Okay, and if you put R here, you will get 1 by R square minus 1 by infinity. Okay, sorry, first integration, then the limit. First integration of 1 upon x square, integration of 1 upon x square is minus 1 by x. right? We all know that x to the power of minus 2. So x to the power of minus 2 plus 1 divided by minus 2 plus 1, that is x to the power of minus 1 with a minus sign, so that is 1 by x. So I hope that at this stage everyone understand this integration is equal to this. When you are starting your PU2, some of you have struggled to understand this integration because integration was not done in mathematics yet. So a lot of you have struggled. When I was teaching, I see many students was not able to understand, sir, why this is so, please explain, etc. Okay, but now I hope everyone is aware. Now this minus is common, so it can come out of the integration, and this becomes plus, and it becomes kq, and here we get 1 by r minus 1 by infinity, so that is equals to kq by r. Okay, now by definition this work done, potential is actually equals to this work done, or potential equals to 1 by 4 pi epsilon naught. Now time for us to put it some suitable dress, q by r. Okay, so this is the potential due to a point charge. This is the expression for potential due to a point charge. Now let's move on. Obtain an expression for potential energy of an electric dipole placed in a uniform electric field. Define the energy density of a charged capacitor. How is energy density related to electric field present between the plates of a capacitor? So here we have an electric field, and in this electric field we have a dipole. And what will happen to this dipole? Dipole will experience a torque, right? If this angle is theta, dipole will experience as a torque, and that torque is given by torque equals to Pe sin theta. If you remember, when a dipole is kept in an uniform electric field, it experiences a torque. Now, if you rotate this dipole by applying some torque of yourself, this is internal torque. If you want to rotate it by some amount, you have to apply an external torque equal to this value. And if you rotate it by a very small angle, say delta theta or d theta, then how much work you have to do? To rotate it by a small angle, again rotation in linear motion, work done is given by force into displacement. In rotational motion, work done is given by torque into displacement. So work done to move rotate the charge by a small angle is given by torque into d theta. Okay, torque into d theta is the work done that you are doing to rotate the dipole when it is kept in an external electric field, and that is equals to Pe sin theta d theta. Okay, so what is the total work done? Total work done is actually stored as potential energy of the system, and that is equals to integration Pe sin theta d theta. Okay, now P and E are constant for a given dipole and given electric field, so they will come out of the integration, and you will get sin theta d theta. And here the limit will be your starting point will be pi by 2 and final angle will be theta. So you are starting at this angle and then you are rotating it to the angle theta. Okay, so pi by 2 to theta. Remember this limit, otherwise it's very simple. If you remember the limit, it will be very easy. So Pe and the integration of sin theta is minus cos theta pi by 2 to theta, or if you put the limit, the potential energy of the dipole is given by minus Pe, minus is common outside. First you put the upper limit, that is cos theta minus cos pi by 2. Cos pi by 2 is 0, so we get potential energy stored is minus Pe cos theta, or potential energy is minus P dot E. Okay, so this is the expression for potential energy stored in a dipole in uniform electric field. Now what about the second part? Define the energy density of the capacitor. So energy density is given by total energy stored in a capacitor. Total energy stored divided by the volume. Total energy stored divided by volume of the capacitor is called energy density of a capacitor, and it is given by half epsilon naught E square. Okay, this is the expression for energy density in terms of electric field. Let's move on. Assuming the expression of drift velocity, derive the expression for conductivity of a material where sigma equals to Ne square tau by m. Very easy question. Okay, very easy. This derivation is very super simple. This question came in your preparatory exam also. So let's see. So first of all, drift velocity expression is given. What is drift velocity? Drift velocity is given by E into small e into capital E divided by m into tau. Okay, tau here, tau is not torque, here tau is relaxation time. Okay, E is charge of an electron, E is electric field, m is mass of an electron. Okay, so this is the expression for drift velocity. You have to declare the variables, okay, because derivation is very simple. Now we also know that current in a conductor is given by I equals to NEA VD, right? Or I upon A equals to NE VD. What is I upon A? I upon A is current density. So current density equals to NE into EE by M into tau, right? If you put the value of VD in this equation, you get this. I upon A is J, current density J. So J is given by I by A, right? Now J equals to NE square by M into tau into E, right? Now from Ohm's law, current density J equals to sigma E. So this is our equation number 1, this is our equation number 2. So comparing, sigma equals to NE square tau by M. Now this is, there is one more way from where you can derive it, but this is the easiest and simplest way of derivation, okay, in terms of drift velocity. So that's why I have used this approach, and if you have used this method, you will get full marks. Only thing, declare the variables and mention that we know current equals to NEA VD. So if you mention and declare all the variables, then you should get full marks. Obviously the derivation, as you see, is very simple. Actually it is a 3-marker derivation, but if the question paper is easy, you might get this as a 5-marker as well. Derive an expression for effective EMF and effective internal resistance of two cells of different EMFs and internal resistances connected in series. So two cells connected in series, epsilon 1 R1, epsilon 2 R2, and we have an resistance R. Okay, now what you have to do, first of all, because they are connected in series, the current should be same in both cases. So whatever current is passing here, the same current should come back over here as well. Now equivalent circuit, what is equivalent? Equivalent means only one cell and one internal resistance is there. The external resistance should remain same. So this is equivalent, this is R equivalent, and the current in the circuit should also remain the same. So this diagram is compulsory. Again, the diagram you have to draw. In this case, the diagram is not compulsory. Okay, some students draw there is a current, there is a wire, conductor, but that is not required. Okay, that this diagram is not super compulsory. If you wish, you can draw it. Okay, electric field is in this direction, drift velocity here. Okay, the simple diagram you can draw if you wish to, but this derivation does not require any diagram. Similarly, this one also, this diagram is compulsory, but for second part, no diagram is required. Now, this is a compulsory diagram. Okay. Now, when the current you are calculating, what you have to do? You have to apply Kirchhoff's laws. Obviously, applying Kirchhoff's voltage law or Kirchhoff's loop rule. Okay, so we can say that voltage drop across this resistance is I into R, and because we are going in the same direction, so voltage drop across this small resistance is I into R2. Okay, and voltage drop across this is equals to I into R1. Okay, so all the voltages are added, and that should be equals to the sum of the EMFs epsilon 1 plus epsilon 2, or IR equals to epsilon 1 plus epsilon 2 minus I into R1 plus R2. Very simple. Take these two on the other side, I is common, and you get IR. So name this equation as equation number 1. Now if you apply Kirchhoff's law in the equivalent circuit, so applying Kirchhoff's law in equivalent circuit, okay, this is original circuit. CKT is the short form of circuit. Okay, in equivalent circuit, what we get? IR plus I into R equivalent equals to epsilon equivalent, or IR equals to epsilon equivalent minus I into R equivalent. So now if you compare equation 1 and equation 2, what you get? So obviously this must be equals to this. So comparing 1 and 2, epsilon equivalent equals to epsilon 1 plus epsilon 2, and R equivalent equals to R1 plus R2. Very simple, easy derivation. Let's move on. Derive an expression for effective EMF and effective internal resistance of two cells of different EMFs and internal resistances connected in parallel. Okay, so here we have two cells. This is also, by the way, important. Do not only practice Kirchhoff's law, Wheatstone bridge, because Wheatstone bridge, there are tendencies sometimes Wheatstone bridge do not come. Okay, so do not only, it is possible Wheatstone bridge might come, but cells in series and cells in parallel are also important. Don't ignore that. An equivalent circuit is given by only one cell and one internal resistance. Now current in this particular case is obviously not constant. Just a second. Yes, so current in this case is not constant. Remember that. Current is, suppose the current in this is I1, current in this is I2, then the total current I is equals to I1 plus I2, but in this particular case the same current I will flow. Okay, so from first KCL gives us I equals to I1 plus I2. Okay, now we will take two loops separately for original circuit. First we will take this loop. Okay, from this loop we can say that I1 R1 plus IR equals to epsilon 1, or I1 R1 plus equals to epsilon 1 minus IR, or I1 equals to epsilon 1 by R1 minus IR by R1. Right, this is for the first case. Okay, for including so loop 1, and for loop 2 similarly we can write I2 equals to epsilon 2 by R2 minus IR by R2. Okay, because they are same we can write it like this, and I1 plus I2 is equals to I, so I equals to I1 plus I2, or equals to epsilon 1 by R1 plus epsilon 2 by R2 minus IR common, and we get 1 by R1 plus 1 by R2. Now let us rearrange this a little bit. So I equals to this, so we will try to find IR. So let us write that. So IR, let us take this IR on this left hand side and write IR into 1 by R1 plus 1 by R2 equals to epsilon 1 by R1 plus epsilon 2 by R2 minus I. Okay, now this I goes to the other side. So we write IR equals to epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2 minus I divided by 1 by R1 plus 1 by R2. Okay, so this is the equation number 1. This is equation number 1. Okay, this is equation number 1. Okay, similarly for equivalent circuit, what we can write? For equivalent circuit, we have already done it in our previous part, so you have to do the same steps again and you have to show that it is equals to epsilon equivalent minus IR equivalent. So comparing 1 and 2, we can write epsilon equivalent is equals to epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2, and here it is IREQ and here we have 1 by R1, so 1 by R equivalent is equals to 1 by R1 plus 1 by R2. So this is the equivalent EMF calculation. Okay, not super difficult, but you need to practice this. This is tricky. This derivation is longer than series 1, okay, and you have to practice it 2 times to master this derivation. Next, the most common derivation, arrive the balance condition of Wheatstone bridge using Kirchhoff's laws, and as usual I am going to do this in the shortest most possible way. So here we have PQRS. Obviously diagram is compulsory. PQRS. So current, say in this one I1, this one is I2, this one is IG, this one say say 3, this one say I4. Okay, so I1 current is going over here and it is dividing into 2 parts, IG and I3. It is I2 is coming from this, IG is coming from this, they are merging and we get I4. Okay, this is I4, this is IG. Okay, now the condition of balanced Wheatstone bridge is, condition is, what is condition? Condition is when the galvanometer does not show any deflection. So that means the current through the galvanometer must be equals to 0. So this IG must be equals to 0. Now if IG is 0, then I1 and I3 must be equal. So therefore I1 must be equals to I3 and I2 must be equals to I4. Okay, if this is the balance condition, no current is being added, no current is being added or subtracted, that means these two current must be equal. Okay, now what? Now applying KVL, now loop you have to name A, B, C, D. So applying KVL in A, B, D, A. Loop A, B, D, A. This is the symbol for loop. Okay, loop number A, B, D, A. So we will start from here and the resistance is P. Okay, the current is I1. So what is the voltage drop? Voltage drop is I1 into P. Okay, now through this IG into G, okay, IG into G, now IG is 0, okay, IG is 0, but there is a G, so let me put that in here as well. And when you are going from D to A, to close the loop, when you are going from D to A, you are going in against the direction of current. You are going against the direction of current. So against the direction of current means it will be minus, and you have to apply I2 into R. And there is no battery or cell connected in this loop, so this must be equals to 0. So we can say I1P equals to I2R, right? This is 0, or P by R equals to I2 by I1. Now you can applying KVL in the loop BDCB. BDCB. Okay, now we are going in this direction. BD, D to C, B to D is Ig into G, that is 0 into G, plus D to C, we are going in the direction of current, so S into I4 or I4 into S. And while going from C to B, we are going against the current, so minus I3 into Q. Okay, I3 into Q, and there is no cell connected, so it will be 0. So I4S must be equals to I3Q. Now we know that I3 is equal to I1 and I4 equal to I2, so we can write I2S equals to I1Q. Okay, or Q divided by S equals to Q divided by S equals to I2 by I1. This is our equation number 1, this is equation number 2. Okay. Now comparing 1 and 2, we can say P by R equals to Q by S, or P upon Q equals to R upon S. This comes over here, R goes here, R and Q are exchanged because they are diagonal. So P by Q equals to R by S. This is the condition of balanced Wheatstone bridge. Now let's move on to the next question. Derive an expression for force per unit length on two infinitely long thin parallel straight conductors carrying current, and hence define ampere. Very common question. So let's do it. So here we have two wires carrying current infinitely long. One of them is say carrying current say I1, another one is say carrying current I2. Okay, this is wire number 1, this is wire number 2. Both of them are carrying current same direction. For now we are assuming the distance between the wire is D. Now because they are infinite, we cannot do anything unless we fix a length. Okay, so that's why we have to take an arbitrary length L. Later on we will obviously remove it. So take some length of say small l. Now what is the force acting between them? First step is to calculate the magnetic field due to wire 1 at the location of wire 2. Okay, so magnetic field due to wire 1 at the location of wire 2, B12, and magnetic field due to wire 2 at the location of wire 1, say B21. So we have to find that. So what is the formula for magnetic field due to a straight wire carrying current? It is given by mu naught by 2 pi I divided by R. So for 1 it will be I divided by D. Okay, this is B12, and B21 will be equals to mu naught by 2 pi. So this formula you have to remember. In case you forget, there is a way to remember it. I will tell you later on. Okay. So what is the way to remember? Just a simple thing, that there is a straight wire carrying current. You consider an Amperian loop of radius say R. Okay, then from Ampere's law it is B dot dl equals to mu naught I, or B is constant, so dl is the circumference of the circle, so that is 2 pi R, that is mu naught I, and from here you can calculate B is equal to mu naught by 2 pi I by R. Okay, so this is the way to remember. In case you forget what is the magnetic field due to a straight wire, I can't remember. So just on right hand side of your page, you just do this small derivation, very small. This generally comes as a 2-marker question as well, 2 or 3-marker question as well. So you anyway you have practiced it. In case you forget, you can remember it like this. Okay, don't make a mistake while calculating the magnetic field. Now if the magnetic field is known, we can calculate the force acting on a wire of length L. Okay, so force acting on say wire 2 due to wire 1 is say F. on 2 due to 1, and this is the force on 1 due to 2. Okay, so F21 is given by B12 I into L sin theta. Sin theta is 0 over here, so that's why sin theta is 90 degree over here. Current and angle is 90 degrees, so that means it will be 1. Okay, magnetic field B12 is in this direction. Okay, sorry, magnetic field is in this direction, so that means the angle is 90 degrees. Okay, it is into the page of the paper. Now this is F12, so now put the value. So F21 is equals to mu naught by 2 pi I1, this is I2, I1 by D into I2 into L, or you get mu naught by 2 pi I1 I2 by D into L. Similarly, if you calculate this one, F12 is equals to B21 into I1 into L. Okay, same length, we are considering same length for both the wires, so we can say that this is equals to mu naught by 2 pi I2 by D into I1 into L. Okay, into L. Now you can reorganize it, mu naught by 2 pi I1 I2 by D into L. So basically you can see that from these two forces are equal, and these two forces are opposite in direction according to Newton's third law of motion. F21 must be equals to negative of F12 magnitude wise, but magnitude wise they are same. Okay, the direction wise they will be opposite, but magnitude wise they will be same. And say these two forces F21 and 12, they will be magnitude wise same, and say this same force we are denoting by small f, capital F, so it's say same. Okay, so F equals to, if you see that if both of the forces are same, right, that's why we are saying the magnitude is same. So we can say that F equals to mu naught by 2 pi I1 I2 by D into L. Do not leave your answer over here. You have to find force per unit length. That means what you have to calculate? You have to calculate small f, which is equals to capital F by L, which is mu naught by 2 pi I1 I2 by D. Okay, so this is independent of L, because L we have assumed only because so that we can apply this force formula. Okay, because force formula requires a length, that's why we have assumed this length. Okay, so this is the expression for force per unit length. And what is the definition of ampere? If you take I1 equals to I2 equals to 1 ampere and D is equal to 1 meter, then whatever is the force per unit length, mu naught by 2 pi, that is a constant. So that's how we define 1 ampere. Ampere is the current when flows through each of the two parallel conductors kept at a distance of 1 meter experiences 2 into 10 to the power of minus 7 Newton per meter force. Okay, so we know that if I1 equals to I2 equals to 1 ampere and D equals to 1 meter, then force per unit length becomes mu naught by 4 pi, mu naught by 2 pi. Now mu naught is 4 pi into 10 to the power of minus 7, so it will become 2 into 10 to the power of minus 7 Newton per meter. Okay, because it's a force per unit length, so Newton per meter is the force per unit length. Now let's move on. Derive an expression for magnetic field at a point on the axis of a circular current loop. This question in my opinion is important this year. It did not come last year, so there is a high chance this will come this year. It was not there in the first paper. First paper the other derivation, this derivation came in the first paper, but anyway it has been came back to back years, so it might come, so that's why you have to practice this one as well. But in my opinion you cannot skip this one, you have to practice this one. So here we have a current carrying loop. Okay, and you are trying to find the magnetic field, say at a distance x. This can be little tricky if you are doing it for the first time, so practice it. So take a small element dl and you have to find the magnetic field due to this element dl at this position. Okay. Yes, sorry. Now what we have to do, we have to take the small element dl, and the angle between the dl and the radius vector is 90 degrees. So when you are applying Biot-Savart's law, remember this angle I dl sin theta that you use, that sin theta is 90 degrees, so it is 1. This angle, by the way, is not theta, it is phi, and if this angle is phi, magnetic field will make an angle with this axis as an angle phi. Now if you consider the two components of this magnetic field along the y direction and along x direction, and if you consider another component diametrically opposite point here, then you will get another component y direction in this direction, and y direction will be cancelled. X direction will be added up, y direction will be cancelled. So that's why we will not consider y direction, only x direction is sufficient. But first, obviously, we have to apply Biot-Savart's law. So magnetic field B dB, obviously small element dB, magnetic field is given by mu naught by 4 pi I dl divided by this r square, right? And suppose this is capital R, this is small x, so small r is actually, according to Pythagoras theorem, capital R square plus x square. So we will put that in a while, not now, but for now this is the magnetic field. Now as I mentioned, only x component is there, so we have to start with the x component. So dbx, or the x component of the magnetic field, is db cos phi. Why cos phi? So this is dB, so this is the adjacent angle, adjacent side, so adjacent component is always cos component, so it will be dB cos phi. Now this angle is also phi. If this angle is phi, this is r, okay, you can calculate the cos phi as well. So cos phi is actually equals to capital R divided by small r, right? Base divided by hypotenuse. So this is phi by r by r. So now put the values, mu naught by 4 pi I dl divided by small r square into capital R divided by r. Okay, now simplify, mu naught by 4 pi I r into divided by small r cube into dl. Now remember, we are not here because of the small element. We have to calculate the entire circle. So to calculate the entire circle, obviously we have to take all such possible dls and add them. That is integration. Okay, that's why when we consider the diametrical opposite point, because we know that ultimately we have to consider the element which is in the opposite side as well. Okay, that's why the y components we have successfully cancelled. Only x component is there. So because we have to calculate the entire circle, we have to integrate. So total magnetic field Bx will be equals to integration, close integration of this. Close integration means starting point and ending point are same. So dbx, and if you see that mu naught by 4 pi I r cube, they are all constant. Only dl is varying along this circle. So mu naught by 4 pi I r by r cube, they will all be common, only we have to write close integral dl. Now close integral dl, you already know, close integral dl is nothing but the circumference of the circle. So this will be mu naught by 4 pi I r by r cube, and close integral dl is nothing but 2 pi into r, radius, capital R. Okay, capital R, because it's a radius. So don't make small mistakes like adding small r over here, or mistakenly adding capital R and small r mistakenly. That will cause some major harm, right? So you will lose marks. So mu naught by 2 I r square by r cube. Now it's time for us to put the value. Now r value we already know. So r is actually r square plus x square to the power half, right? Because it's a square root. Now if you cube both sides, you will get through the power 3 by 2. So we can write that x component of the magnetic field, actually this is the only magnetic field left, y component already cancelled, so that's why we are writing Bx mu naught by 2 I r square divided by r square plus x square to the power 3 by 2. This is the derivation. Now after this derivation there are two special cases. They might add this as a extra information, that what if try to calculate the magnetic field at the center. Instead of asking on the axis, if they say on the center, you have to start with the axis. Okay, you cannot directly calculate the magnetic field at the center. So we have to start with the axis, and then for center, what we can say, x equals to 0, right? Obviously magnetic field will be 0, at the center this distance x will be 0. Okay, so if you put x equals to 0, then you can get the magnetic field at the center, which is given by Bx equals to mu naught by 2 I r square divided by r cube. So r square to the power of 3 by 2, 2 cancels and you get r cube. Okay, now you can simplify this as Bx at the center, Bx x component at the center is actually given by mu naught by 2 I by r. Okay, so this is the formula for center. One more possibility is there, that is the distance is very far, the x is very far. In that case, if the distance is very far, you just need to do you need to ignore the r square in the division. Top portion you cannot ignore, bottom portion you can ignore, and if you ignore that, you will get x cube. That's it. Okay, but generally that will not come. If they add any extra part, that will be at the center. Okay, that will be at the center. So in that case, this is the derivation. In case, just have an idea, in case they ask you about a point at a distance, then r will be ignored, and in the division we will get x cube. Okay, so like the dipole one. Okay, the distance is very far away compared to the distance of the dipole. So here the radius, if the radius is smaller, then the distance, distance will lead. In top we cannot cancel, but in the division we can cancel, we can ignore. Okay, not cancel but ignore. Now next, deduce the lens maker's formula. Okay, lens maker's formula, very common. Now from ray optics chapter we are expecting a numerical, but if there are chances of coming any derivation, there are two derivations I recommend. One is lens maker's formula, another one we will explain just a while. So lens maker formula, the diagram is compulsory. Obviously whenever I am drawing the diagrams are compulsory. Okay, so suppose this is a lens, okay, and the radius of curvature of this first surface is r1, radius of curvature of the second surface is r2. Okay, we have an object kept at a distance u, and we are getting some image at a distance v. Focal length of this lens is, say, f. Now so this medium, say refractive index n1, refractive index of this medium is n2, refractive index of this one is again n1, because it's a lens, so both sides must have the same refractive index. Okay, and the material of the lens is n2. Okay, if this is n1 is air, if the first and second medium is air, then you can put n1 equals to 1, but otherwise start with general formula, then we will move on to the specific formula for air. Okay, now to solve that, we have to remember the equation that we are using for a complete refraction through a spherical surface. Okay, so this was u, if you remember, this was u, this was v, and this was n1, this was n2, and we realized that the radius of curvature of this surface was r. Okay, then we know that n1 by u minus n2 by v equals to n2 minus n1 by r. Okay, so this is the general formula for refraction at a spherical surface. Now here, the main thing here, we have two spherical surfaces. Okay, one is curved like this, another one is curved like this. So when the object is moving through the first surface, only the first surface, it will form an intermediate image, say somewhere here. and we are saying this distance is v dash. Okay, because obviously first surface will form an image somewhere and the second surface will finally form the image where we are looking at. So first surface will form an image somewhere here, that will be v dash. So v dash will be actually acting as the object for the second surface, obviously, and here it will be r1. So v dash is the intermediate object distance. You have to write the thing that due to the first surface, let the image formed at a distance v dash from the lens, and the final image is formed at a distance v due to the second surface. Okay, so this is the equation number 1. Now for the second surface, object distance is v dash, and our starting medium is refractive index n2. Right, our starting medium is refractive index n2, because we have arrived at this surface. Now we have to move through this lens and then go to the second surface, right? So it will be n2 by v dash minus n1 by final image is formed in n1. So final image is formed in n1, so n1 by v, and that is equals to n2, sorry, not n2 now n1 minus n2 by r2. Okay, so remember always this is the thing, where is u? U is in the medium n1, so u is in the medium n1, that is that's why n1 by u. Where is v dash? V dash is actually in the imaginary second medium, so that's why it is n2. Similarly, v dash is in the secondary imaginary n2, v dash is imaginary n2. Okay, and that is why when we are applying this formula, you have to remember that wherever is the object is, that should be accompanied by its own refractive index. Refractive index by object distance equals to refractive index by image distance corresponding to where the location, final location. Okay, now what you have to do, simply, very simple, you have to just add them. This is equation number 2, just add them. So if you add, you will see that this is minus n2 by v dash, this is plus n2 by v dash, so this and this cancels and we get n1 by u minus n1 by v. I think I made a mistake. It will be, it is 1 by v minus 1 by u, right? So I made a mistake, sorry, extremely sorry. So it will be n2 by v dash n1 by u. Okay, and here it will be n1 by v minus n2 by v dash. Okay, so this and this will cancel, 1 by v minus 1 by u, that is the formula, right? So that's what we are trying to prove. So here it will be n1 by v is positive and n minus n1 by u, which is negative. So let us put it like this, and here we will get now if you take n2 minus n1 as common, you will get, so you cannot actually take n2 minus n1 common, because here we have n1 minus n2. So this one is positive 1 by r1, but this one will be negative 1 by r2. Okay, if you take a negative sign common, this will be n2 minus n1, right? So that's why it is there is a minus sign, or 1 by v minus 1 by u equals to n2 by n1 minus 1 by r1 minus 1 by r2. Okay, so n1 we have taken common and divided this term, so n2 by n1 and n1 by n1 is 1. Okay, clear? So this is the thing. Now next what? Next is, this is not done yet, we have to find the focal length. Do not put this as 1 by f. Okay, do not put this as 1 by f. You have to write if u equals to infinity, then V is equals to F. So if the object is at infinity, the final image forms at F. That is the definition of focal length, right? If the object is at infinity, parallel rays falling on the lens, and the final image we obtain at the focal length. So now you put that satisfying in this equation 3, we get 1 by F minus 1 by infinity equals to N21 minus 1, 1 by R1 minus 1 by R2. What is N21? N21 is the relative refractive index of medium 2 with respect to medium 1. Okay, now 1 by infinity is 0, so we can write 1 by F equals to N21 minus 1, 1 by R1 minus 1 by R2. Important derivation, so do practice it. Diagram is compulsory, and some write-up is also necessary to explain why it is V dash, why you are taking this as V dash. Okay, so here we are adding them. Now let's move on. Derive the expression for refractive index of the material of the prism in terms of angle of minimum deviation and angle of the prism. So this is the second derivation that I recommend. Now in this derivation, geometry is very tricky. So how can you avoid the geometry? First of all, you have to draw a lot of diagrams also, but geometrical derivation is not required. It is only a 5-mark question, but what you have to do, first of all, the diagram you have to draw cleanly. Okay, so you need to draw the diagram neatly. This is the triangle ABC. This is the cross section of a prism ABC. You have to mention this is the incident ray, angle of incidence. This is the first refracted ray. This is the second refracted ray. Okay, the diagram is very, very important. This is internal angle R1. This is internal angle R2. And if you extend that, you get the angle of deviation delta. Okay, the angle of the prism is A. This is the angle of the prism. Okay, so this diagram you have to start with. This is the first diagram, and then you have to mention that from geometry, you don't need to do the geometrical derivation, but you have to write from geometry delta is equals to I plus E minus A. So if you know this is I, this is E, then I plus E minus A gives you the delta value. Okay, now A equals to R1 plus R2. This can also be proved from geometry. So these two can be proven from geometry. Now if you plot, this graph is compulsory. This graph is compulsory. If you plot angle of deviation versus angle of incidence graph, observing I versus delta graph, we can see that the angle of minimum deviation occurs when the angle of incidence is equal to emergent angle, that is I is equals to E and R1 equals to R2 equals to small r. Okay, so this is the condition for minimum deviation. Now once you are done with this, then you can say that therefore delta m, that is minimum deviation, is equals to 2I. So I is equals to E, so I and E are same, so I plus I, 2I minus A. From here you can calculate I, and A is equal to R1 plus R2, so R plus R, that is 2R. So you can say that R is equal to A by 2. Okay, now from Snell's law we can write the refractive index of the prism with respect to surrounding is given by sin I by sin R, and that is equals to sin, instead of I you have to put this value A plus delta m by 2, and instead of R you have to put A by 2. Okay, so this is the not very difficult derivation, but diagram you have to draw these two diagrams, which can be complex at times. So that's why if you have if you are confident with the diagrams, do go for it. If you are not confident about the diagram, you can skip this derivation. Now let's move on to next question. Two coherent waves of same amplitude and constant phase difference undergo interference Obtain an expression for resultant displacement. Number 2, mention 2 uses of Polaroids. Now this is a 3 marker, 3 plus 2 question. Now mention the uses of Polaroids I have discussed in 2 marker question. I will tell you, I will not give you the in writing, but I will tell you the uses. But if you want in writing, you can check my 2-3 marker videos. There I have explained the mention the uses of Polaroids. Very simple, easy uses. Okay. Anyway. So two coherent waves of same amplitude. So two coherent sources means we have, say, source number 1 y1 given by a sine omega t, and another wave having same amplitude, that means it will be a sine omega t plus phi. Phi is the phase difference. Phi equals to phase difference. Now when they superpose according to the superposition principle, according to superposition principle, the resultant displacement is y r equals to y1 plus y2. Okay, so resultant displacement is given by y1 plus y2. So what is y resultant then? Y for this diagram is not required. So it is a sine omega t plus a sine omega t plus phi. Okay, now you can take a common, so you can write a common sine omega t plus sine omega t plus phi. Okay, let me use third bracket. Now this is sine a plus sine b formula, simple sine a plus sine b formula. So a into sine a plus b by 2, so that is 2 sine, so it will be, so 2 sine, that's why we have to write 2a. Now why this 2 coming? Because sine a plus sine b equals to 2 sine a plus b by 2 into 2 sine a minus into cos a minus b by 2. Okay, so sine omega t plus omega t plus phi divided by 2 into cos omega t minus omega t minus phi by 2. Okay, so this is the expression for resultant displacement. Okay, now so you can simplify this. Omega t plus omega t is 2 omega t, 2 omega t by 2 is obviously omega t, and we will be left with phi by 2. So we can write this as 2a sine, I make a mistake over here again, sorry for that, there is no sine over here, obviously we have substituted that. So 2a sine omega t plus phi by 2, and here we have omega t cancels, we have cos minus phi by 2. Now cos, for cos minus and plus does not matter, cos of minus theta is cos theta, so we can write this as 2a cos phi by 2 sine omega t plus phi by 2. So now if you see that in the resultant wave, this is the new amplitude, this is the resultant amplitude, and this is the sine omega t term that was there in terms of phase difference. So phase difference is phi by 2 and new resultant is 2a cos phi by 2. Okay, so this is the answer for this. Obviously you don't need to do anything else. If they ask you about intensity, then you have to take the square of this and you have to write, okay, 4a square cos square phi by 2 or 4i phi by 2, but that is not there, not required. And uses of Polaroids, Polaroids are used in sunglasses, Polaroids are used in 3D glasses to watch 3D movies. Okay, so these are the very common uses of Polaroids. Next, using Huygens principle, arrive at the law of reflection for a plane wave. Now, Huygens principle is very important. You have to state Huygens principle again in 2-3 marker question series. I have explained Huygens principle. You can check that out. Okay, so using Huygens principle, law of reflection. So how to do that? Obviously, to prove that, you have to take 2 rays of light which is falling on a mirror, and by the time this ray falls, another ray yet to reach the mirror. So first ray already reached the mirror, and this ray is reaching only up to this point. So this angle is 90 degrees. Okay, and this is actually angle of incidence. And if you join these 2 points, because they are perpendicular, you will get the incident wavefront. So this is incident wavefront, say AB. Now by the time the ray of light reflected back to some point, this ray reaches up to this point. Okay, so this ray, by the time this ray reaches over here, this ray goes to over here. So this is the angle of refraction, R. Okay, and if you join this point and that point, you will get the reflected wavefront. Okay, reflected wavefront. So this is, say, CD. CD is the reflected wavefront. Okay, now one property of wavefront, if the ray is making an angle I, the wavefront will make an angle I with the plane of reflection from where this is reflecting. And similarly, if the angle of refraction is R, then the reflected wavefront will make an angle R with the reflecting plane. Okay, so this will be I, this will be R. Now we know that in case of reflection, I is equals to R. So basically what we can say, if this is R, then they will also be equals to I from law of reflection. Okay, but obviously we need to prove that. We need to prove this I equals to R, that is the law of reflection. So don't put I over here. Okay, so just for your information, that even though they are equal, you need to show that. Now what? Now we have to take the triangle ABC and ADC, and we have to show that they are congruent. If they are congruent, these are the similar angles and they should be same. Okay, now how to show that they are congruent? Say the speed of light in this medium is V. Okay, speed of light in this medium is V. So the time taken by the light to reach from A to D, time taken by the light to reach from A to D is, say, T. Then time taken by the light to reach from B to C also be T. Okay, because the light is traveling in the same medium, and the wavefront is designed such a way that they are all connected through phase. So they were in phase, these 2 points should also be in phase. That means the distance travel has to be same because they are in the same medium. That is the basic idea. Okay, so we can say that what is the distance BC? Distance BC is equals to speed of light into time. And what is the distance AD? AD is again the same thing, speed of light into time T. Okay, time is very important for light to maintain their phase. Okay, time is very important for the light to maintain their phase. So BC and AD has to be same. Okay, so we can say that from these 2, we can say that BC is equals to AD. Now this angle is, this is a wavefront, so AD is a wavefront, so that means this angle is 90 degree. Again, CD is also a wavefront, so wavefront, this angle will also be 90 degree. Okay, wavefront always makes an angle 90 degree with the ray. No matter what type of wavefront it is, even if it is a spherical wavefront, it makes an angle 90 degree with the plane. Okay, so remember that. So wavefront always makes an angle 90 degree with the plane. That's why this angle must be 90 degrees. Now let us consider triangle ABC and triangle ABD. Okay, for ABC, AD, BC equals to AD. Okay, angle ABC equals to angle ADC. Okay, and AC common. That means from side angle side, we can say that triangle ABC is congruent to triangle ADC. Okay, these two triangles are congruent, and because they are congruent, their similar angles has to be equal. So angle BAC, therefore angle BAC must be equals to angle DCA. Okay, so that means angle I equals to angle R. So this is the law of reflection. Easy derivation. If this derivation comes, it will be definitely coming with the state Huygens principle and hence proof. So Huygens principle you have to remember, as I mentioned, I have done it in my 2-3 marker section. Next, using Huygens principle, arrive at the Snell's law of refraction at a plane wave. Now this is slightly tricky. Diagram is slightly tricky. Again, same thing, 2 rays of light falling on a plane, and when this ray reaches over here, the second ray was here, angle is 90 degrees. Okay, now arrows are very important because wavefront do not have arrows, but ray of light does have arrow. Now by the time this ray reaches over here, okay, this ray entered the second medium and it bends somewhere here. Okay, so this is the refracted light. Now here we are not trying to prove I equals to R because it's Snell's law, so you have to prove Snell's law. So this angle is I. So as I mentioned, the wavefront will make an angle I. This angle is R, then the refracted wavefront will make an angle R with this. So this is the incident wavefront AB. This is the reflected wavefront CD. Okay. Speed of light is different in these two mediums. So speed of light, say in this medium is V1, speed of light in this medium, say V2. Obviously two different medium. Refractive index of this medium, say N1, refractive index of this medium, say N2. One of them can be air, but we are assuming in general formula. So general formula is you have to consider N1 and N2. Okay, now what? So we will start with obviously this angle is 90 degrees, this angle is also 90 degrees. Now we will start with the fact that the time taken by the light to reach from B to C, if this is T, the same time will be taken by light to reach from A to D, that is also T. Okay, so BC in this case equals to V1 into T, and AD in this case is V2 into T. They are not same. Okay, these distances are not same. There is no congruency required in this derivation. Now what we have to do, we have to find sin I and sin R. That's it. Okay, because Snell's law talks about sin I and sin R. So sin I equals to, what is sin I? Sin I is perpendicular by hypotenuse. Perpendicular is BC by hypotenuse, which is AC. And what is sin R? Sin R is actually equals to, again this is R, so that perpendicular by base, perpendicular by hypotenuse, perpendicular is AD divided by AC. Hypotenuse is same, this is 90 degrees, so this is opposite side hypotenuse, this is the 90 degrees, so opposite side is hypotenuse. Now let's put the values of BC. BC is V1 into T divided by AC. Okay, and AD equals to V2T by AC. Now we will try to find sin I divided by sin R. So that is the condition of Snell's law. This is equals to constant and that is equals to refractive index. So we will be doing that only. So we will get V1T by AC divided by V2T divided by AC. So obviously by AC will cancel, TT will cancel, and we get V1 by V2. Okay, now what we will be doing, we will be slightly changing the order. We will write this as C by V2 into V1 by C. So we have multiplied and divided by C. This is the refractive index of the second medium, and C by V1 is the refractive index of the first medium. Absolute refractive index is defined by speed of light in vacuum divided by speed of light in that particular medium. So this can be written as, so sin I by sin R can be written as, this is N2 divided by N1, right? This can be written as C by V2 divided by C by V1. Obviously this, if this comes in the division, the order will be inverted, so C by V1, okay, so that V1 goes up, right, when we simplify it. So we get sin I by sin R equals to N2 by N1, or we can say N1 sin I equals to N2 sin R. This is the general form of Snell's law. This is the generalized form of Snell's law. So hence proved. Okay, now next, remaining three derivations are easy. Okay, obviously you can guess which of the three. What is the rectifier? Explain the working of a full wave rectifier using a neat circuit diagram. Draw is input output waveforms. So an rectifier is an electronic device that converts alternating current AC into direct current DC. So this is the circuit diagram, and now you have to explain each cycle individually. So during the positive half cycle of the AC input voltage, AC input voltage, the upper half of the transformer secondary, that is the upper half, this means point A, is positive, and diode D1 becomes forward biased and conducts, allowing the current to flow through the load resistor RL. Diode D2 is reverse biased and it does not conduct. Okay, so this is full wave rectifier, so two diodes are there. Okay, second is in the negative half cycle of the AC input. During the negative half cycle of the AC input voltage, the lower half of the transformer secondary winding become positive. Diode D2 becomes forward biased and conducts, while the diode D1 is reverse biased and does not conduct. Current again flows through the load resistor RL in the same direction as during the positive half cycle. This is very, very important point to mention. If you don't mention it, you will lose 1 mark. Same direction is very, very important. And in this waveform diagram, you can show only one wave, that is fine. So diode D1 conducts, this is diode D2 conducts. Okay, so this is how the diagram should be drawn. In your textbook, they have given an inverted waveform for this, which is completely unnecessary because this is the input wavefront and this is the output wavefront. Okay, so that's why you just need to show one input and one output only. Okay, so two input is not required to show. Next, what is half wave rectifier? Explain the working of a half wave rectifier using a neat circuit diagram. Also draw input output diagram. Half wave rectifier is an electronic circuit that converts alternating current AC into direct current by allowing the current to flow only during one half cycle of the AC input signal. The other half cycle is blocked, so only half of the AC wave form is used. That's why it is called half wave. Now, positive half cycle of the AC, again positive, negative both you have to mention. During the positive half cycle of the AC input, the P side of the diode is positive. With respect to the N side, the diode becomes forward biased and conducts current. Current flows through the load resistor RL in one direction and the voltage across the load is positive. During the negative half cycle of the AC input, the P side of the diode becomes negative with respect to the N side. The diode is reverse biased and does not conduct. No current flows through the load resistor RL and the output voltage is 0 during this half cycle. Okay, so the circuit diagram is very simple. Only one diode is there. Okay, generally full wave rectifier comes almost every year. There are few tendencies, few years exceptional where half wave rectifier has come. Okay, so this is half wave rectifier. So here you have to show the input output diagram of the AC signal. Now remember that apart from this, there is one more question which might come. As I am mentioning, it might come, it never came in the past year, but every year this question is given in your model question paper. Every year, year after year, this question is given in your model paper, but it never came in the final exam. So there might be a chance that this question will come this year, so be prepared. This is an easy question. Write three differences between intrinsic semiconductor and extrinsic semiconductor. Draw the energy band diagrams of N-type, P-type semiconductor as temperature T greater than 0 Kelvin. So definition, a pure semiconductor with no impurities is called intrinsic semiconductor. Extrinsic semiconductor is semiconductor doped with a small amount of impurity to improve conductivity. Charge carriers, equal number of electrons and holes, unequal number of charge carriers, majority carriers electron in type, hole in P type, and minority carriers. Conductivity, low conductivity at room temperature, high conductivity due to doping which increases the charge carrier. Now in the band diagram, make sure you have to show the donor level, which is donor level, for N type, and for P type you have to show acceptor level. In N type, more number of electrons are present in the conduction band and very less number of holes are present in the valence band. Okay, so this is valence band, this is conduction band. Okay, similarly here it is valence band and this is conduction band. In case of P-type semiconductor, there are more number of holes present in the valence band only and very few electrons are present in the conduction band. Remember that, okay? Holes are located in the valence band, electrons are located in the conduction band. But otherwise, both have electrons present in the valence band. Okay, free electrons are present in conduction band, free holes are present in valence band. Okay, so these are the major thing. Otherwise, the diagram is very simple. And the energy gap, you can show the energy gap is 0.01 electron volt. Here it is also 0.1 to 0.05 electron volt. Okay, so this is a new question. It never came, as I mentioned, but it always there in your model question paper. So please study it. In case it is coming in your exam, you should not say that, okay sir, you said half-wave full-wave rectifier will come and it did not came. It's not like that. Also, the PDF of this lecture will be available on our WhatsApp channel, and don't forget to download it. WhatsApp channel link is given in the description section. Every time without watching the complete video, you come, sir, where is the note, where is the note? Notes links are shared in our WhatsApp channel, so if you have not joined, you will not get the notes. So join the WhatsApp channel, link is in the description, and once you join, you will be able to check the old messages as well. So scroll down a little bit up. Generally with the daily updates, we are giving you the WhatsApp the link from where you can download the PDF. So go there, download the PDF, use it, and if you have any other question, mention in the comment section below. Okay, and if you feel that this video is good for you, then please like this video, and if you are watching our channel for the first time, what you have to do? Subscribe, right? Also remember, these 20 derivations are enough to get 3 derivations common in your final exam. You don't need to practice anything else. These 20 derivations are sufficient for your board exam. That is my guarantee. Okay, if the question does not come, you can come and hit me after your exam, but not before that. First study these 20 derivations. They are very, very important, and obviously fixed, almost fixed. 3 derivations will come out of 20, and I wish you all the best. I'll be meeting you in live sessions very soon,